Okay, in this video we're going to look at contact bounce, and that's in reference to mechanical electrical switches. Now here you see a little push button switch mounted on this box. Now that's a little human interface into a microcontroller, usually through one of the GPIO lines. Now it could indicate an on-off condition, or a yes-no decision, or maybe even counting data. Now the microcontroller expects to see clean signal transitions from the switch, which is not always the case, and that's what we'll look into in this video. Okay, here's a little schematic diagram of the push button switch and the pull-up resistor and the output to the I/O, the GPIO of a microcontroller. Now when the push button is open, the I/O output will be high into the microcontroller, as we can see here. Now when you press on the push button, it will go low for the duration of the press till it's released, and it will go up high again. Now this is a clean signal that the microcontroller wants to see. But in the real world, we're going to get this, as seen in the bottom diagram. When the push button is pressed, we're going to get contact bounce, where the contact is going to bounce, and we're going to get this chatter happening for about 10 milliseconds until it settles down along here. Then when we release, we're going to get a little bit more chatter until it settles down into the high level. So somehow we have to clean up the chatter on the press and the release into the microcontroller, and we'll look at some techniques to do that. Okay, here's a crude model of a push button switch. Here are the two contacts inside the switch, and these would be the terminals leaving the switch where you hook up your wires, and this would be your shorting mechanism. So in this position, the push button switch is open, and in this position it would be closed, and you would have current running through the switch. So what happens in slow motion when you depress on the push button switch, you would get contact bounce. You would get bouncing action like that. And the duration of the bounce is about 10 milliseconds before it settles down, depending on the type of switch. Okay, in front of me I have a whiteboard, and I have a marker in my hand, and I'll demonstrate contact bounce on the whiteboard. So what I'll do with the marker, I'll strike the board once, and you'll see the pattern that it makes, and you can see a distinct bounce. You'll see two distinct hits even though I was striking it once, and that's basically what's happening to the switch contacts when you activate and deactivate a switch. Okay, solving contact bounce can be done in hardware or software. I prefer hardware so I don't have to worry about it when writing code. It's up to the individual. So we'll look at some hardware circuits. Now most of these circuits assume that the contact bounce has a duration. So at some point it stops, and that's around 10 milliseconds. Now some switches have longer duration bounce times than others, so every switch is different. So the first circuit we'll look at is an RS flip-flop, and when the switch is put into the set position, the output goes high, and no matter how much the switch bounces, it won't affect the output unless the switch is put into the other position, into the reset position. So this is probably the best circuit for contact bounce elimination. The only drawback is you need a single pole double throw switch, and normally when you're using a circuit with a push button switch, it's a single pole single throw switch. Now you can also use actually a flip-flop, 4013D flip-flop, and just use the set reset pins. So it's basically the same circuit, except that you're using actually a flip-flop instead of using NAND gates to make up a flip-flop. Now this is the circuit that I used the most. It's the MC14490, and it's a contact bounce eliminator, and the input is single pole single throw push button switches, and there's 6 circuits in this chip. It's a DIP chip. So basically you have one external component, that capacitor that runs the internal oscillator, and then there's a shift register inside that shifts from the left to the right output, and every time bounce happens it resets the shift register. So once the bounce settles down, the shift register will get to the output and the output will go high. Now this chip is hard to get. It's still available, but it's pricey. So Maxim has come out with a Max 6816, which does the same thing, except you can't get it in a DIP package. So this is the one that I use the most if it's available. So next we'll look at some circuits that use RC time constants to clean up contact bounce. Okay, here's a couple of circuits that use RC time constant to clean up contact bounce on a switch. And you can see here a resistor and a capacitor in series. And the capacitor is fed into the input of an inverter, a 4093 or a 74C914. And that's a Schmitt trigger inverter. It has to be a Schmitt trigger for the circuit to work properly. So the capacitor charges up through the resistor to VCC, and that's fed into the input of the inverter, so the output will be low. Now when the push button is pushed, it will short the 0.05 microfarad capacitor to ground to 0, and now force the output of the inverter high. Now if there's any chatter on the switch, if there's any bounce, it has to go through the RC time constant. So the RC time constant is set up so that small bit of contact bounce will not have enough time for the capacitor to charge up to trigger the input of that inverter to change the output. Now a lot of engineers don't like to put a switch across the capacitor to discharge it. They'll decrease the contact life of the switch. So there's a variation of this circuit where they put a resistor in series from the capacitor to the switch. So that will limit the current through the switch when it's discharging the capacitor. I'll still put a diode across the 470 ohm resistor, so the charge time to the capacitor will be fast, but the discharge through the switch will be through the 470 ohm resistor. So that's basically the same circuit, except it just uses another component for the switch contacts. Okay, next we're going to look at how to eliminate contact bounce using software. Now when your code is running, you don't want to make any decisions between this edge and here, because you'll get erroneous data. So as soon as you detect the first edge from high to low, you could do nothing for 10 milliseconds. You could put in a little delay and then read the switch again, and if it's low you could continue on. Same when you come to the button release. As soon as you see the first high edge, you could do nothing for 10 milliseconds. You put in a 10 milliseconds delay and then read the switch again, and if it's high you continue on. So that's one way you could eliminate contact bounce using software, and we'll look at an example. Okay, here's a bit of code that will debounce a switch that's hooked up to pin 2 of the Arduino Nano, a little push button switch, and every time you press and release a button you'll toggle pin 13, which is the LED that's on board the Arduino Nano. So this is all the code you need. This is written in fourth, variation called E-fourth, and it's very compact code, and basically this is all you need. So where we start, it's going to read pin 2, and if it's low, it's going to get a 1 for yes, and that's going to be put on the stack. It's going to wait 10 milliseconds, and it's going to read pin 2 again, and if it's low, you'll get another 1 put on the stack. And then it will compare the two, and if they're two the same, like a 1 and a 1, say yes and yes for the pin 2 being low, they'll go down and it will toggle pin 13, and then it will go into a loop while the button is pressed, waiting for it to be released. And when it's released, it's going to go back up to here again. Now pin 2 low, it will get a 0 because now it's released, and it will wait 10 milliseconds. And we'll read it again, it will get a low, so now you got 2 lows. So that will continue on to circle around. It will bypass this if statement because they're both low. Now say we had a contact bounce that was more than 10 milliseconds. So the first time it comes through, it will get a low. So you get a 1, waits 10 milliseconds, and then say you get a high. So they won't be the same. So it will repeat and go back and try it again until it gets 2 in a row of the same. Then it will continue on and toggle the LED and repeat the process all over again.